Hello, hello everyone. Welcome to Physics Today. Um, here's what we're doing right now. We're going to start with a warm up. As you may or may not know, so what I'm currently trying to do is I'm currently trying to stream this to YouTube because if I do, it automatically records it. So that way you can see what we're doing later, what we've done today later, if you want to review. So I'm just testing it out, trying to see if it works well or not. So don't be alarmed, nothing crazy. What we're doing today is we're going to start off with the warm up. So as usual, join a table group in Discord. Otherwise, I'll just put you in a breakout room, which is fine too. In the Zoom chat, what I want you to do is I want you to answer the following. I want you to answer, what is acceleration due to gravity? Then I want you to answer this other question in the Zoom chat. If my self-esteem was an object and it's in free fall, how fast is my self-esteem falling after 6 seconds? Last but not least, if a Bugatti Veyron accelerates from 0 to 100 kilometers an hour in 2.5 seconds, I want you to find what is the Bugatti's acceleration. For this, I want you to use meters per second and meters per second squared. So just make sure you're using those units. Otherwise, you can get started, and then when you're ready, start putting some answers in the Zoom chat as well, and then we will see what we can do. So remember that let's see, how many answers do we want? Let's see if you can get 5 or 6 answers today. So what I want you to think about is remember that the Bugatti Veyron is accelerating from 0 to 100 kilometers an hour. We want to make sure our answers are in meters per second squared. So just make sure you're looking at that. And then for the self-esteem in free fall, you may want to think about how long I have started. So when my self-esteem in free fall, you can assume that at the moment it starts, it's not moving at all. It's at 0 meters per second. And so I just want you to figure out how fast my self-esteem is falling after 6 seconds. Let's see if we can do that. And then let's see what we can get for the Bugatti Veyron as well. When you're ready, you can start putting some answers in the Zoom chat, and let's see what we can get. Let's take another 3 minutes or so. I think we can do it in 3 minutes. Let's see what we get. Let's see, when you're ready, just start putting some answers in the Zoom chat, and we will see what we can get. So I'm going to start working through it on the board. So let's first start off with the acceleration due to gravity. So the acceleration due to gravity is just g. So g for gravity. So this is a very important thing to remember. The acceleration due to gravity is 10 meters per second squared. What this means is that every 1 second, an object speeds up. By 10 meters per second.
Isn't it 9.8?
It is 9.8. Yes, sorry. We used 10 in my other class, so sometimes I forget. It is 9.8, correct. Thank you for reminding me. Okay, so that's acceleration due to gravity. So for the second problem, what we're gonna do is we're gonna try to figure out how fast my self-esteem is falling after 6 seconds. So let's sort of take a moment to review what acceleration actually means. So acceleration just means how much our velocity is changing over how much time. Okay, so let's take a moment to look at how much our, let's take a moment to review, okay, what is our acceleration? Or our acceleration in this problem is just g, right? Because the only thing that's causing our acceleration is gravity, because we are in free fall. So we're trying to find how much my velocity has changed, so we don't know that yet. But we do know how much time, because I've been falling for 6 seconds, so my change in time is 6 seconds. Okay, so let's do some math out. 6 times 9.8 is 58.8. So we get that my change in velocity is 58.8 meters per second. And because I initially started at 0, I forgot to write it on the board, but initially started at 0. So that, oh, this should be negative 58.8, I'm sorry. And this should be negative 9.8. So after 6 seconds, my change in velocity should be negative 58.8. And since I started at 0 meters per second, my final velocity should be just negative 58.8. Does that make sense, how I did that? So for the last problem, what we're going to do is we're going to look at how fast this Bugatti Veyron is accelerating. So first off, what we want to do is we want to do a little bit of conversion. So in terms of conversion, we first want to convert kilometers an hour to meters per second. So I said 100 kilometers an hour, which is 100,000 meters. In an hour, there are 3,600 seconds. So 100,000 divided by 3,600. This gives us 27.7 meters per second. So this is our velocity. What I did here is I converted kilometers an hour to meters per second. The next step I have to do is to divide our, okay, so let me write this out. So this is our velocity. And so what we want to do is we want to figure out what our change in velocity is over our change in time. So our change, since we initially started at 0 meters per second, our change in velocity is 27.7 meters per second. My change in time, since I did it over 2.5 seconds, is on the bottom. So I get my acceleration is 11.11 meters per second squared.
Wait, where did the 3,600 or?
So this is, here, I'll do this, 100 kilometers an hour. Kilometers per hour is 100,000 meters per 3,600 seconds. So what I did here is I just converted kilometers an hour, 100 kilometers an hour, to 100,000 meters per second. 100,000 over 3,600 meters per second. So this is just the conversion here. Does that answer your question?
Yeah.
Okay. So does anyone else have any questions about this? Does this sort of make sense, what we're doing here? Yes, no, maybe so. Okay, so here's what we're gonna do next. So on Canvas, there is an assignment called Asteroid Mission Part 6. So this is picking up where we left off last Friday, when we looked at some asteroids. So we're gonna pick up where we left off, and we're going to start adding in acceleration into our scenarios. So, to look at our to look at this asteroid mission, it's on Canvas called Asteroid Mission Part 6. We're going to do it in class. So it's not going to be for homework if you don't finish it in class. I don't think we are going to finish it in class, unless we're just flying through it. So we're going to do Part 6 in class. So the way it's going to go, there are, I think, 6 or 7 questions. Each one gets a little bit harder, as usual. But it should be, I would say, so we're gonna do all of it. We're gonna do what we're gonna do is we're gonna go through a couple problems, and then I'll do a problem on the board, and then do a couple more, and then I'll do a problem on the board. So that way everyone sort of is on the same page with it. So for now, so I'm gonna give you a couple minutes to start with question 1, and then I'll do question 1, just because question 1 is a good way to start, and then I'll leave, and then we'll for the rest of the. We'll sort of do it as question by question. So, okay, so if you open up Asteroid Mission Part 6, it's on Canvas. I'm just going to share my screen right now, just so you can see it. So what we're first going to do is we're going to try to take a look at question 1. What I first want to do is write down a general function. So this one I'm just going to do right now. Just because last year I think people were a little confused. So I'm going to write this down here in the left corner. So the general function that we want to use for modeling positions with asteroids. So if you remember last time, the general function we used was this one to model it with no acceleration. So the general position was x of t is x naught. X naught is our initial position. X of t is our position with respect to time. And what we did here is we added a velocity times time term. So basically this is saying the position of an object is its initial position plus its change in position, which is velocity times time. So this is like no acceleration. No acceleration.
We can't see your screen or your board.
Oh, yeah, I forgot. Hold on. Let me see. That is, oh, you know what? Here's one. Okay, can you see it now? So what I was writing is I'm writing in the left-hand corner here. So this, okay, so this is what I'm writing. Okay. So the position with respect to time is x of t. X of t is equal to its initial position, which is x sub naught, initial position, plus its change in velocity, change in position, which is its velocity times time. So this is with no acceleration, which means that this velocity is constant. Okay, so now what we're going to do is we're going to add in our new revamped function to model the position of an asteroid with acceleration. So this is 2.0. 2.0 is x of t, very similar to last time, is equal to x naught plus v naught plus 1/2 at squared. So this is the general formula that's very important to remember. So v naught here, this is our initial velocity.
Could you indicate which one is a t and which one is a plus?
Let's see, what's the best way for me to do that? Here, I'll add like a little.
Make the T's capital T's.
Is that better?
Yes, thank you.
Okay, so x sub naught times plus v sub naught times t plus 1/2 at squared. So v naught is our initial velocity. This is important because our velocity is going to be changing throughout the whole thing. So v naught here is our initial velocity, not velocity with respect to time. These two are going to be different things. Okay. A is our acceleration, and A is going to be constant. We don't do non-constant. We don't do changing accelerations in this class. So A is the constant acceleration, and T is time. So this is the function we're going to be using to model the position of an asteroid. Very, very, very important.
What is x of 0 or x? What is the x stand for?
Perfect. Good question. So x of naught. So naught in general in physics, and I think in math too, when you have a subscript 0, this means that it means initial. So I'll write it down here. This is initial displacement. In general, this sub naught means initial. Yeah, so anytime I write naught, it just means initial. So x of naught is initial displacement plus our initial velocity times time plus 1/2 at squared. So this is a very important function that we're going to look at when we're using our modeling our position of an asteroid. Does that sort of, did I do a reasonable job of explaining that? Okay, so that's sort of to start off with in terms of figuring out the most important function. So what I'm going to do here is I'm going to give you a few minutes to start question 2, and then I'll work through question 2 in front of the class. That way everyone can see where we're going. But I do want to give you a chance to do some practice. Before we get started, does anyone have any questions? Okay, I'm going to get started, and then I'll go around and answer the questions you may have. Yeah, so we're gonna try to finish as many as we can, but for now, just start working on question 2, and then I'll do it in front of the class. Hello, everyone. I'm going to do question 2 on the board. That way everyone can sort of see how we can do this. That way no one's confused on this. So what we're going to do here is we're going to first start off with our general equation for modeling the position of any object with acceleration in it. So let's do this. Let's first start off with our equation. So in our equation, what we have is we have a bunch of stuff. We got our x of t. This is equal to our initial position plus our velocity times time plus 1/2 a times t squared. Okay, so in our initial problem, what we have here is we're given a few things. We're given that the asteroid is initially starting at 10 kilometers above the surface of the Earth. Now, the key thing here is that up is positive. So if the asteroid is 10 kilometers above the Earth, it starts at an initial position of positive 10,000. Okay, now this next term right here is very tricky. There's a very important difference between velocity and acceleration. Velocity is how fast something is moving. Acceleration is how fast that movement speed is changing. So in the first problem, what I've told you is, hey, the asteroid is initially not moving. So if it is initially not moving, there is 0 velocity. However, it is in free fall. So when an object is in free fall, it means it is only under the influence of gravity. That means there is no other source of acceleration other than gravity. So what I can do here is I can say, okay, instead of 1/2 at squared, I can replace this with a 1/2 gt squared, because g is our acceleration due to gravity. Okay, so this is very important. This is a very important idea. When an object is in free fall, you can replace this a with the g, because g is acceleration due to gravity. And this is a very important distinction here. The object is not moving, so its velocity is 0, but it is accelerating. So you can have a 0 velocity and some sort of acceleration. And that's a very important distinction. We want to make sure we're understanding the difference between the movement speed and how fast that speed is changing. Okay, so let's simplify this a little bit more. What we'll get is x of t is 10,000. G is negative 9.8. So what we're going to do is we're just going to replace this with a negative 4.9 t squared. I just multiplied 1/2 with g. So I get negative 4.9 t squared. Does anyone have any questions about how I did A? That sort of makes sense. Okay, so what we're going to do for B is we're going to do the same thing. We're just going to take this here, but instead of 0, the asteroid is initially falling. It does have initial velocity and is falling at 17 meters per second. So what we're going to do here is we're going to take our position function, x of t. This is 10,000. The initial velocity, 17, but the asteroid is falling initially. It's not going upwards initially. So this is going to be a negative 17. We're going to throw in a time here. And then our acceleration is the same. So it's just going to be negative 4.9 t squared. So the only thing difference between A and B is that there's initial velocity. The acceleration is the same because both are under free fall. And that's a very important distinction as well. Okay, so let's talk about C. So for C, what we're going to do is we are going to show us we're going to take a look at these graphs. So if I were to draw a graph of acceleration, so acceleration is constant. That's what in physics, in this class, what we'll do is we're always looking at a constant acceleration. So our acceleration is just going to be a line across here at negative 9.8. Our velocity here. So our velocity starts at negative 17 because we're falling downwards. So this is negative 17. And it's speeding up. It's becoming more negative. So it's going to be a downward sloping line. And then last but not least, our position versus time. So this is the hardest one. These two are sort of a little bit straightforward. Velocity and acceleration have a linear relationship. So if we were to draw out if we were to write out this equation for velocity, so here's the equation for velocity and acceleration. Our velocity is our initial velocity plus acceleration times time. So this is our function for velocity. Initial velocity plus the change in velocity. Notice how this looks a lot like mx plus b, which we know is a linear equation. So this is what this velocity versus time graph is going to look like when there is acceleration. It's just going to be like a linear graph. It is a horizontal line because whenever something is constant, it means it's not changing. The graph is always going to be horizontal. Now, last but not least is this one, this position versus time. So, and if we look at here, what it looks like is we have a quadratic relationship between x and t, which means that our graph is going to be curved. So the most important thing here is I'm not really going to be looking at for the, your actual like can you like get every point correctly? What I'm really looking for is the shape. The shape is very important. So initially we're starting off at an initial position of positive 10,000 on the top. And the thing is, it's going downward. So our position is decreasing, but it's decreasing at a faster rate because it is accelerating. So our graph is going to look like this. Notice how initially it's not moving as fast, and by the end it's moving very, very fast. So this right here shows us one of the two possible sort of graphs you can have with acceleration. There's a very important distinction here. There are two graphs. One is concave up and one is concave down. You have concave up here, a concave down here, and then you have concave up here. So in our gravity, in the problem we just did, we have a concave down graph. And a concave down graph, what this means is that we have a negative acceleration. Our acceleration is negative because our velocity is becoming more negative after every second. And what we have here is we have a concave up graph. And this means that our velocity is becoming more positive. So usually you're not going to have a negative time. Usually it might look more like, you might have more something like this, and then you might have something like this, potentially. For this graph, you might have something like this. And so anytime the shape is a concave up, it means that there's a positive acceleration. And every time your shape's like this, is a negative acceleration.
Could the graph have a positive initial velocity and have a negative acceleration?
Yeah, so you can have a positive initial velocity and then have a negative acceleration. So let me show you what a positive initial velocity and a negative acceleration would look like. So what I'm going to do is I'm going to show you, this is going to be a positive V naught negative acceleration. So if it's a positive V naught, what it means is its position is going to be initially going up. However, a negative acceleration means that is going to start decreasing. So it's going to look like this. Here, you have a positive initial velocity because it's going upwards, but because the acceleration is negative, it's going to be turning this positive slope more and more and more negative. So by the end, it's going to look like that. So it's still going to be concave down. Does that hopefully do a good job of explaining question 2? Yes, no?
I have a question for the graph for the second graph. Does that like just not include the acceleration? Is it just negative 17t?
So it's not, so this is a velocity versus time graph. So this is not negative 17 times t, because negative 17 times, this is a graph that shows us that our initial velocity is negative 17, and every second it's becoming more and more, it's going to decrease more and more and more.
Okay.
Yeah. Anyone else have any questions about that? Okay, so if you have any questions, we're going to keep on continuing with questions 3 and 4, and then we'll see how everyone's doing as well. So class is finishing in a minute, so you do not need to complete the Astro mission for homework. You do not need to do it. I don't want anyone to panic about it. It's also not graded. It's just an in-class assignment. Your only homework is just to finish the project if you haven't already. If you need to turn it in later, that's also okay. Just let me know. Otherwise, you're free to go. So have a nice weekend. If you have any questions, you can stick around and ask me them. And I have office hours again from 2:40 to 3:40 as per the usual. Anyways, have a nice weekend, and I'll see you all next week.
Thank you.
Thank you.
Nice
Thank
weekend.
you.
Thank you, Mr. Yu.
Thank you.
All right, thank you, sir. Have a nice one.
You too.
Also, I submitted my project City Skyline Part 4.
Perfect.
Well, good luck on grading those, I guess.
Oh, I know. You think doing it was hard, but you have to grade them.
I mean, is it really our fault? I would say that you brought it down on yourself. You gave us the
I
assignment.
did bring it from. I have to test my spreadsheet abilities based on yeah.
Just give everyone an A plus. You know.
Yeah. That's the easiest way to do. Or I do the thing where I throw down all the papers down the stairs, and then whoever lands the farthest gets an A. And whoever
All
lands
right,
the
just keep my paper on top.
Okay. Did anyone? I know some people have some questions for me.
Have a nice one, sir.
See ya. Kiara, you have a question for me?
Oh yeah, I did. I just don't understand how to do the instantaneous velocity graph in level 4 because it just like there's so many different, like every time it reaches an intersection it's like 0 and then but only for like 1 minute, and then it goes back up to being constant at like whatever the speed 45 or something, and it's just like happens so many times. I'm not sure how to exactly like do the graph then.
Just do it for like a certain segment of the path. So do it for like, I don't know, like 100 seconds or so. I don't know exactly how long your whole journey took, but just do it for a segment of the graph, and that's fine.
Oh, okay, that's a lot easier. And then also, what about for the, because mine was like, it was like 100 minutes, I think. And so I'm not sure how to also write the like velocity equations because there's going to be so many different parts.
So for that one as well, do it for I would say just pick the part where your velocity changes the most, like if you go from bus to metro to whatever, just do it for like a certain segment of it, and then that's fine.
Oh, okay, great, thank you.
Yeah.
And then this is the last thing, just quickly, because I didn't understand the wording of the instructions. It said that to plot both directions, north, south, and east, west, in the instantaneous velocity graph. Is that contained in like the same line, or is it?
No. So you do two separate graphs. One for your north south displacement and one for your east west displacement.
Oh. Okay. Cool. That
do it
makes
on the
sense.
same line?
What? I haven't done it yet because I wasn't sure. Because I thought velocity was like on the actual streets. I didn't realize it was just the two components of the vector.
Yeah.
Okay, that makes sense. Cool. Thank you.
Okay.
Have a nice day.
You too. Olivia, did you have any questions for me?
Yeah, so I was confused on how to do the last question on the city skyline homework. 11C, it's talking about if a train increases by speed increases by 1.2 meters per second every second until it reaches maximum speed, how long does it take to reach maximum instantaneous speed?
Okay, so what was your question about on that?
I just don't know how to do that because I don't think I did right because I just divided the maximum speed by 1.2 meters.
That's right.
Oh, but then I got like 14 hours.
So let's see. So 17 miles an hour is about 34 meters. No, that's not correct.
Well, I thought it's like 33 miles per hour for the metro, right?
Mm-hmm.
And then to meters or kilometers, it's like 53 kilometers about per second, and then I transferred that to meters, which is like 53,000.
But you realize that's 53,000 per hour.
Oh, and then oh yeah,
So
okay.
you did your formula is correct, but you just have to make sure you're converting it properly.
Okay, like
Also, just a tip, you can just type in whatever miles per hour to meters per second on Google and they'll do it for you.
okay.
You don't actually have to do the whole math out.
I did the miles to kilometers on Google.
Okay, okay.
But yeah.
Yeah, okay, cool. Oh, God.